the guesswork for you guys, so you don't have to like guess like, oh, I have to get whatever to pass. So, but yeah, so if you do more homework, the projections will lower. And obviously, if you've done really well, if you've done all your homework and you did well, I would say the projection there would be like a, if you, for example, wanted I don't know why you would want an F, but if you wanted an F, it would say impossible to get an F or impossible to get a C if you've done really well. It's basically by Wednesday for sure, because I want to give you guys enough time to be able to like, uh, I guess, I mean, you should always plan to get 100 next time, but like at least be able to like realistically show where, okay, I'm gonna go for the B or for the A or for the C, right? So, which means that I am quarter of the way done with the grading exam 2, and I basically am gonna spend all day today and tomorrow finishing it up. And since it's much shorter this time, because last time I kind of overwhelmed myself, I had like, I had 4 problems, and each one I had like problems A, B, C, and that was already adding way too much on me. But yeah, so you should have those projections by Wednesday for sure, and you should be able to like plan. All right. Any questions before I move or go? Nope. Okay. All right. So we shall now continue with the last stuff to talk about in at least undergraduate linear algebra. And again, that was the eigenvalue problem, right? So I posed the question. Suppose you had a matrix A, you multiply the vector on it, and it spat out the vector as scaled up by some lambda, or down if it's less than 1. Okay, so how do I find all these vectors that basically does that under A, right? And I basically said, okay, so how can we find these V's here? Or even in particular, how do we even find this lambda, right? So I just said, okay, well, let's kind of solve it like an equation. I started off with AV equals lambda V, subtracted it over to the other side, factor out a V, and then from there we use some linear algebra stuff that we knew, like when does this equal 0 if V is not 0? Well, we use the fact that determinants, if the determinant of this thing is not 0, then this is 0, then this thing will not be 0, right? So basically we're at this point right now. We got this nice little formula here. So, oh, come on. Sorry, hold on a second. I have to do this again. So at that point, all you have to do is basically do exactly what I have there to solve eigenvalue problems. So let me, you don't need that, we don't need that. Yes, perfect. So we solve this thing to get our eigenvalues. Okay. Okay, so let's do an example. Let's see, we haven't done any examples here. Find the eigenvalues of, say, A equals, I don't know, 2 minus 12, 1 minus 5. What is this? Well, we're going to do exactly what I said here. We're going to take the determinant of that. So finding A minus lambda I, we get A minus lambda I is going to equal to, well, 2 minus 12, 1 minus 5, subtracted by, well, it's going to be just lambda and it's the identity times, so it's just going to be this thing. So 2 minus lambda minus 12, 1 minus 5 minus lambda, right? Okay. So now we have this new matrix. Finding now the determinant of A minus lambda I, you literally just take the determinant of this thing right here. And since you guys for sure already know how to find determinants. For this one, for example, I mean, this is a 2 by 2, so it's just going to be um, uh, the product of the diagonal minus the first diagonal minus the second, right? So let me take this over here. All right, so let's see. Okay, what is this going to equal? Well, it's just going to be equal to 2 minus lambda times minus 5 minus lambda plus 12, right? Okay, well, now solving this, I mean, you can distribute this thing in, you get minus 10 minus 2 lambda plus 5 lambda plus lambda squared plus 12. So if you simplify everything, that should give me plus 3 lambda. And that should be plus 2. Yeah, right, that should be plus 2, yes. Okay, setting this, now you set this equal to 0, right? You get lambda squared plus 3 lambda plus 2 is equal to 0. So, I mean, just factor this, you get lambda plus 1, lambda plus 2 is equal to 0, which means you get that lambda is equal to minus 1 minus 2. So these are the eigenvalues now. So which means that, so these are the eigenvalues. Okay. Okay, so you find the eigenvalues, which, I mean, like you said, it's a very straightforward computation. There's nothing really too hard about it. I mean, just take the determinant, you solve a polynomial in, I don't know, degree 2, 3, 4, it doesn't matter. You use whatever you know from college algebra to find the roots, and those are your eigenvalues. Okay. Well, so now we know how to find the eigenvalues. So how do we find the eigenvectors? Well, it's as simple as once you find what your eigenvalues are, you just plug them back into the original equation, right? A minus lambda I times V is equal to 0, right? So, I mean, now you know what your matrix is, right? As soon as you know what this is, then you know how to solve for that. I mean, that's just stuff we did in chapter 1, just RREFing stuff down to a real reduced echelon form and expressing your solution in either, in coordinates or in vector form. We're gonna use the vector form because we're gonna see that that's gonna give us our eigen. Well, it's gonna give us the basis for our eigenspace, but yeah, I mean that's literally so as soon as you know that, then you know what this would be, right? Okay, so let me just summarize that whole process into this. So theorem 7.1.2. So let A be a n by n matrix. Then 1, a eigen value is a scalar lambda such that the determinant of a minus lambda I is equal to 0, 2. What is it? Oh yeah, the eigenvectors of A corresponding to lambda. Sorry, hold on. Oh, perfect. Sorry. Corresponding to lambda are the non-zero vectors, or rather solution to a minus lambda I v is equal to 0. Okay, so I mean, this summarizes what we did, or the first part is what we already did. The second part is what we're going to do right now. So now let us find the eigenvectors. So taking the example from last time, what we're going to do is you're going to see all we have to do is plug it in to that a minus lambda I times v equals 0 and solve for v. So, all right, so example 7.1.2, find the eigenvectors of I guess a equals what is it? 2, -12, 1, -5. So from the last problem, so from previous example, we know that lambda 1 is going to equal to what did I say? We were -1, and I mean, it doesn't matter which one I choose. It's just going to be to be 1. But so it's just these two, right? This is what we found it to be. So plugging into a minus lambda I v is equal to 0, we get what? Well, if I so let's do lambda equals 1. Okay. So if I plug that one in, what do I get? Well, I'm gonna get well, it's gonna be 3. So that's the other one's gonna be so it's -12. That's 1. So it'd be 5 plus 1, which is -4. And you so it's gonna be this times v1, v2 is equal to 0, 0, right? So I mean, you can just augment this just to save yourself time. And if you RREF this, well, then you'll just get, well, 1, I can scale the first row by, well, yeah, this would just better be just 1 minus 4, 0, 0, 0, 0, right? Okay, so here's my v1, here's my v2. This means that v1 is equal to 4v2, right? And v2 is free in this case, right? Okay, so now you solved it, right? So now how do I express this in vector form? So let me take this thing. So expressing solution in vector form. We have, so v is going to equal to v1, v2. What is v1? Well, v1 is 4v2. What's v2? Well, v2 is free. Factor out the v2, you get 4 and 1. So my solution to this is that it's every constant multiple of 4, 1. So now so I guess if you were to like, I guess see videos on how people compute this, they usually just pick v2 to be 1 and then you get 4, 1, right? Or you could have literally just picked it to be 2 and you get 8, 2 as well. Well, you can do that. I mean, that'll give you the eigenvector as well. It's just going to give you either the reduced form of the eigenvector or some constant multiple of the eigenvector. But it's, I mean, you can choose on any of those to be your eigenvector. But if you express it this way, it's much easier to see what's going on. But here, this would be the eigenvector, you can say. So this is going to be the eigenvector, okay? So for lambda equals -1, the eigenvector is 4, 1. Okay. Where's this? Let's do lambda 2 is equal to -2. So do the same thing, right? We're going to do the same thing here. So if I do I guess -2, what do I get? I should get, I think it's here somewhere. So hold on. So -4, 12, -12, 1, and then -5 plus 2 would be -3, which is full. And so yeah, so just, I mean, you can just set it in augmented form already. RREF this, what are you gonna get? Well, you can just say 1 -3, 0, 0, 0, 0. So that means that V1 is going to equal to 3 V2. So in other words, V in this case is going to equal to V1, V2, oops, which is just going to be 3 V2, V2, and V2 is free. Factor V2 out, you get 3, 1. So this thing is your eigenvector as well. Okay. So the solutions are, I don't know, so lambda equals, for lambda 1, the eigenvector is going to be 4, 1. And for lambda 2, which is -2, the eigenvector is going to be 3, 1. Okay, there you go. And there you go. So that's how you find eigenvalues and eigenvectors. Now, so going back to the original eigenvalue problem, what should happen if I multiply the matrix A onto this vector here? So what was the original question I asked, right? What should happen if I do 8 times this 4? Yeah, it's just gonna scale 4, 1 by what? But by the eigenvalue, -1, right? So if I multiply A on this vector right here, how am I getting the augmented matrix? So I mean, so remember, I'm trying to solve this right here, right? So plug in lambda equal 1 to this guy, to plug this guy into here. Okay, I'm gonna get A plus I now, right? So do A plus I. So I mean, literally just this is gonna go to 3, and this is gonna go to -4, right? So now you have this new matrix equation that you need to solve for. Well, instead of writing it this way, just get this augmented form, right? Yeah. Okay. No problem. Yeah. So and again, I guess going back to my question, what happens if I do a times this guy? It scales it by what? -2, right? This will scale it by -2. So that means that so we answered the eigenvalue problem. So we found every vector that gets scaled by some scalar multiple. Um, now that you get, I guess, kind of see, let's talk about a few more things. Um, just a few more, I guess, little nice little tricks, or not tricks, but like I guess things that you might want to see. So by the way, this was a 2x2, right? You guys know how to take the determinant of a 3x3, I hope, right? If anything, you should probably be able to do that. I mean, it's the same thing. Instead of a 2x2, you're going to get a 3x3 with lambdas on the diagonal, and you have to take the determinant of that using the cofactor expansion or whatever way you want to do it. Obviously, once it gets to 3x3, if I give you a 4x4, then I'm just being mean to you guys. So I'm not going to do that to you. So 3x3 is probably the biggest you'll expect. But again, the problem isn't. I don't want you guys to be like bogged down by the computations. Like, who cares about that? Like, what we're trying to actually learn is the conceptual stuff, right? But yeah, so I mean, you do the same thing no matter what size the matrix is. The only other thing I guess we should mention is, like, I guess some I can say some facts. If, let's say, A, which is an n by n matrix, is a upper or triangular matrix, then the eigenvalues are just the diagonal entries. Okay, so literally, if it's upper triangular or lower triangular or just diagonal, the eigenvalues of that matrix are just what the diagonal entries are. Okay. Um, well, what's another one? So let's say it's a vertical. Um, well, honestly, I think that's really the only other trick you can do. I guess you can also say that the. Oh yeah, that's right. Yeah, here's another one. So if A, I guess, is a n by n so hold on, give me a second. Yeah, because the book definitely doesn't mention this, so maybe I should put anything about it. So the determinants out here, the traces here. So okay, yeah. So I guess I have to mention some stuff first then. Um, some facts, and I guess I should say definitions. So this is a fact. The polynomial that the results from the determinant of a minus lambda I is called the characteristic polynomial. Okay. Yeah, we'll go through the final example review together. What's another one? Right. I guess let's say let's just put it this base. This so if A is a 2 by 2 matrix, um, then the characteristic polynomial is given by lambda squared minus the trace of A lambda plus the determinant. Oh yeah, we'll be going over the final exam review for sure together. So yeah, so if you have that, if you have a two, I mean you have a general formula for the for in by in case, but I don't think it's really that helpful. But basically, for this one, you can always get the characteristic polynomial from just doing this. I mean, it's not that hard. It's not very it's not too hard. So I guess yeah. So let's trace. So this is the trace. So I don't know. So maybe I should say so the trace of a matrix A is just the sum of the diagonal entries. Okay, so it's just you just take the even if it's not if it's just any n by n matrix, you just add up the diagonal and that's a trace. Okay, so I think that's enough for all that stuff. Who cares about all that? It's literally just more busy work that I don't really care about. The more important things is this. So now, okay, so now that we have these things, I mean, now you know how to compute the eigenvalues, eigenvectors of matrices. Let's talk about more important things about them. So the eigenvectors, they if you take the eigenvector, right? You take the span of this eigenvector. The space that it creates is called the eigenspace um, for that eigenvalue. So let's talk about. So let's do that. So definition. Let A be a n by n matrix and lambda and V. Okay, maybe we should talk about that. So sometimes you can get multiple eigenvectors out of a single eigenvalue, uh, which we'll see. We'll definitely see more of that here in a bit. But this is what I'm saying. So here, let me write this down as a warning here. So we can get multiple eigenvectors from a single eigenvalue. And all that, I mean, you can get them basically if you have two free variables. Remember how we solve our system? Remember, if you get two free variables, you're gonna get like like a v1 with a vector plus a v2 with a vector, because those two would be free. So those two would be the eigenvectors. I mean, so it's like again, it's like solving the. But again, if you don't know what I'm talking about, well, we'll see examples of that. But anyway, so what I'm saying is, so let's say lambda is a eigen value of A, and v1 through vk is a eigenvector, or eigenvectors of lambda, are its corresponding eigenvectors. Then the eigenspace of lambda is, we call it e's of subscript of lambda, which is going to be the span of v1 through vk. Okay. So, as you might expect, this is well, I mean, this is a subspace, right? So, so let's see. Yeah. So I mean, so let's see. So let's see. I want to take the eigenspace. Okay. So one more thing. If v1 through vn is all eigenvectors of A, then this space right here, which is I guess V, such that V is a eigenvector of A union the zero vector. Oh, well, actually no. Let's just take this. Is the eigenbasis of A. Okay, so we have two things: eigenspaces and eigenbasis. So the only reason I'm bringing this up is because so after basically we're done computing maybe one more example of an eigenvalue and eigenvector. We're gonna see where this is applied, because I mean right now it seems like kind of like a weird question to ask, like AV minus equals lambda V, like who cares, right? So we're gonna actually see where it's applied, and we need to know what the eigenspaces are, how many elements, the dimension of the eigenspace as well, and also so we need to know all these pieces in order to be able to like do something called diagonalizing matrices. All right, so let's see. Let's do maybe one more. Yeah, let's do one more example. Yeah, for example, yes, perfect. So let's do one more example. And this would be 7.1.3. So find the eigenbasis for A is equal to 2, 1, 0, 0, 2, 0, 0, 0, 2. And the dimension of each eigenspace. Okay. So first thing you want to do is you want to find the eigenvalues and eigenvectors. So let me ask, what's the eigenvalues of this? What should you immediately like see that this is? Sorry? Yeah. So it's 2, and there's only 2 in there, right? So that means that the only eigenvalue here is 2. Now, you see it 3 times there because it actually has multiplicity 3, which we'll talk about in the next section. So multiplicities, well, we have 2 things called algebraic multiplicity, which means how many times the eigenvalue appears, and a geometric multiplicity, which is again related to the eigenspace, the dimension of it actually. But anyway, so here lambda is equal to 2, right? Okay, well, we only have a single eigenvalue. Let's find our eigenvectors. So if I do a minus 2i v is equal to 0, well, this is just going to give me the matrix 0, 1, 0, 0, 0, 0, 0, 0, 0, augmented with 0, right? Well, this is immediately going to give me v2 is equal to 0, but v1 is free, and v2 is free, right? So how do we express the solutions here? So we have v1, v2, so maybe I should keep doing this one, this stuff here. V is equal to v1, v2, v3. Well, we know v2 has to be 0, and v1 and v2 are free, right? So now just split them up. v2, 0, 0, plus 0, 0, oops, and that should be v1, not v2, v3. Well, this is just going to give me v1 times 1, 0, 0, plus 0, v3, 0, 0, 1. So now these things right here are your eigenvectors. So you see how this single one gave me 2 eigenvectors? Well, now if you were to do the exact same thing, remember I told you on some YouTube channels, they just tell you, oh, we'll just pick v1 equal 1 and v2 equal 1 or whatever, right? Well, yeah, you would do that, but then you would get the vector 1, 1, 0, which is just a single eigenvector, which is not going to give you the 2 that are here, right? So here's the example of having a single eigenvalue but having multiple eigenvectors. Okay. Again, and this is going to be a very important thing here in this next section, which I will go through now. So, well, this next section is called 7.2, diagonalization. Okay, so first things I want to talk about. One is the first definition. Suppose the algebraic multiplicity of a root of, let's say, just lambda to the n, let's just put it in words with the characteristic polynomial of the polynomial of a polynomial. is the I guess, how should I say it? So maybe say something like, so the algebraic multiplicity of a root of a polynomial is the degree of the factored form for that root. So meaning, let's say you had a polynomial. So let's say you had a polynomial, and you factored it out to be the x plus 1 squared, and then you had another one, x plus 3 cubed, and you factored it, and it was this, right? Well, here obviously the solution is x equals -1 and -3, right? So, but here the degree is 2, so we say that this thing has multiplicity 2. Here the degree is 3, so this thing has multiplicity 3. That's all that means, okay? So that's the algebraic multiplicity of a polynomial. Factor it, whatever it factors out to be. Look at the degree that that thing has. That's the multiplicity. Okay. The geometric multiplicity of a eigenvalue, in this case, lambda, is the dimension of the of its corresponding eigenspace. Meaning the dimension of E lambda, right? So take the eigenvalue, right? Plug it into that A minus lambda I in augmented form RREF. Let's say you get out 3 eigenvectors. Well, the number of eigenvectors is basically the geometric multiplicity, right? That's basically what is equivalent to saying dimension of the eigenspace. So in other words, i.e., the number of eigenvectors of lambda. Okay, that's literally all that means. Perfect. Now we are finally ready to discuss what diagonalization means for a matrix A. So basically, what it is another factoring form. So if you remember back in maybe chapter 2 or so, we talked about the LU decomposition or LU factorization. We took the matrix A and we split it up as a multiplication of 2 matrices, right? Well, diagonalization it has this, basically the same type of spirit to it. You take a matrix A and you factor it into 3 different matrices this time, one of which is a diagonal matrix. Okay. So definition, and that should be almost what it is. So let's say A be an n by n matrix with real values. A is diagonalizable. I can spell it right. If there exists a invertible matrix P and diagonal matrix D, such that what? Well, A is equal to P, D, P inverse. Okay. Basically, if you can express it this way, A is diagonalizable. Now, this is what it means to be diagonalizable. I have not told you what P, D, and P inverse is, right? This definition, how as is useless. I mean, how, it doesn't tell me how to find D or P. Well, I mean, you're exactly right. It doesn't tell you anything about that. However, there's a result, a theorem out there that basically says that, well, I'll just finish up with this, and next time we'll talk about the other things, diagonalizing linear transformations. But basically, the theorem basically says what P is the columns are made out of the eigenvectors of A, and the diagonal entries are made out of the eigenvalues of A. So that's basically what I mean PD would be. And then you, in order to find P inverse, you just take the inverse of P, right? But anyway, so that's what we're going to talk about next time. I'll let you know when the next homework session is going to be. But any questions, comments, or concerns? Yeah, for sure. Here, I'll send it right now. Okay, so let's see. Hold on. The 7th, right? So it's going to be the 7th of May. Yeah, 7th of May. It's all day. It's going to be comprehensive. Oh, yes, that's it. Yeah, I'm sorry about that. Hey, just, yeah, just email me again. Yeah, just to remind me. Yes. Okay, hold on. I'm sending you. But it'll be comprehensive, everything from the beginning to what we're going to end at Friday. Okay, I sent the notes, so you should all get it now. All right. I'll see you guys later then. Any other questions? Just probably sometime next week, maybe Monday and maybe Tuesday. I might do it. But yeah, I think those will be the review days. Yeah, for sure. Have a great day, guys.